There exists a galaxy so baffling, so contradictory to everything astronomers thought they knew, that its very existence feels like a cosmic paradox, an object that openly defies the rules of cosmology. This is NGC 1052-DF2, a galaxy that appears to be missing almost all of its dark matter, the mysterious substance believed to make up most of the universe's mass and act as the invisible glue that binds galaxies together. Its presence is like discovering a skyscraper standing tall with no foundation, or a clock that ticks with no gears. Astronomers have spent decades building models of the universe that depend on dark matter being absolutely essential. Yet here is a galaxy that seems to reject that principle entirely. It shouldn't exist by any logical standard, and yet it does, floating in space like a riddle waiting to be solved. The discovery of NGC 1052-DF2 was not just another tick on the endless list of galaxies catalogued by astronomers. It was a revelation that shook the very foundation of astrophysics. In 2018, Peter van Dokkum, a professor of astronomy at Yale University, and his international team of researchers revealed the existence of this enigmatic object. Their work began with the Dragonfly telephoto array, a revolutionary instrument built specifically to search for faint and diffuse galaxies that traditional telescopes would overlook. Unlike the towering giants of observatories like Keck or the Hubble Space Telescope, the Dragonfly array consists of a series of commercially available telephoto camera lenses, optimized with special coatings to suppress scattered light. This unique design gave it the ability to capture extremely faint, low-surface brightness objects, the kinds of structures that often slip through the cracks of more conventional surveys. It was while surveying the region around the giant elliptical galaxy NGC 1052, located about 65 million light-years away in the constellation Cetus, that Van Dokkum's team noticed something strange. Amid the background of faint galaxies and interstellar structures, they spotted an unusual smear of light. It didn't look like a typical galaxy. There was no bright, dense core, no spiral arms, no sharp features that galaxies usually display. Instead, it appeared as a ghostly, spread-out collection of stars, almost like a loose scattering rather than a structured system. At first glance, it was the kind of object that might have been dismissed as an artifact or noise in the data. But the Dragonfly team was cautious, meticulous, and curious. They decided to investigate further. The team's first step was to measure the galaxy's brightness and size. What they found was extraordinary. This galaxy was roughly the same size as the Milky Way in terms of physical dimensions, stretching across about 60,000 light-years. But when they compared its luminosity to other galaxies of similar size, it was shockingly dim. The stars were not densely packed together, but rather scattered sparsely across an enormous region, giving it an almost transparent appearance. Even stranger, the galaxy appeared unusually calm. There was no sign of vigorous star formation, no spiral density waves, no massive central bulge. It looked like a hollow shell of a galaxy, as though some of the most important ingredients were missing. At this stage, astronomers could still think of NGC 1052-DF2 as just another example of an ultra-diffuse galaxy, UDG, a relatively new class of galaxies known for their faint appearance and ghostly structures. UDGs are notoriously difficult to study because of how dim they are, but they had been discovered in clusters before. However, the real shock would come when Van Dokkum's team began measuring the motions of stars and star clusters within DF2. The motions of stars and globular clusters provide a direct way to estimate the galaxy's total mass, since faster motions indicate stronger gravitational pull and therefore more mass. The expectation, based on every galaxy studied so far, was that DF2 should contain vast amounts of dark matter. But as they began carefully tracking the velocity dispersions of bright globular clusters within the galaxy, the numbers refused to match expectations. The stars weren't moving nearly as fast as they should if dark matter were present in large quantities. Instead, their velocities suggested that the galaxy's total mass was almost entirely explained by the mass of its stars alone. In other words, DF2 appeared to be a galaxy with little to no dark matter at all. This was a shocking moment. To put it into context, dark matter is thought to make up around 85% of the matter in the universe, with galaxies themselves believed to be cradled within massive halos of dark matter that provide the gravitational framework needed for stars and gas to collect and form galaxies. Every galaxy studied before this one, even the faintest dwarfs, showed a huge dark matter component. But here was a galaxy that seemed to be operating without it, defying decades of theory. The announcement of DF2's discovery sent ripples across the scientific community. When Van Dokkum presented the results in March 2018, the astrophysics world was stunned. Some were immediately skeptical, suspecting that there must have been a mistake in measurement. Others argued that perhaps the galaxy was not as far away as the team had estimated, and if it were closer, its apparent brightness and structure would be explained differently. But Van Dokkum and his colleagues stood by their data, insisting that they had carefully analysed the distances, the globular clusters, and the velocities involved. The discovery also highlighted the strengths of the Dragonfly telephoto array. This wasn't a discovery that would have been easy for larger traditional telescopes, since DF2 was too faint and diffuse to stand out against the glare of background light. Dragonfly's specialization in low surface brightness detection meant it was uniquely suited to catch sight of this kind of ghostly structure. What seemed at first like a pale smudge turned out to be one of the most controversial and groundbreaking finds of modern astronomy. For Van Dokkum personally, the discovery was exhilarating. He described DF2 as a galaxy you shouldn't be able to see, noting how transparent and fragile it looked compared to normal galaxies. But beyond the poetic appearance, the implications were far more profound. If DF2 really lacked dark matter, then either something had stripped it away in the past, or, even more intriguingly, perhaps galaxies don't always require dark matter to exist. This possibility opened a Pandora's box of questions that astronomers are still grappling with to this day. At the time, though, the team knew they were walking into controversy. They published their findings in Nature, one of the most prestigious scientific journals, aware that their claims would face immediate scrutiny. And they were right. The announcement ignited a firestorm of debate within the astrophysical community. Was this truly the first galaxy without dark matter? Or had the team fallen prey to some subtle error in measurement or interpretation? Either way, the discovery of NGC 1052-DF2 marked the beginning of a scientific mystery that has yet to be solved. What started as a faint smudge in the sky had become a challenge to some of the most fundamental assumptions about the universe, forcing astronomers to reconsider the very nature of galaxies and the role of dark matter in shaping them. When astronomers first laid eyes on NGC 1052-DF2, what struck them most was not just its unusual physics, but its eerie visual presence, or rather, its absence of one. Unlike the dazzling spirals of the Milky Way, the radiant ellipticals of galaxy clusters, or the compact brilliance of dwarf galaxies, DF2 looks like something out of a cosmic horror story. A nearly invisible wisp of starlight adrift in the void. It belongs to a peculiar class of galaxies called ultra-diffuse galaxies, UDGs, which are characterized by their faint, spread-out structure. But even among UDGs, DF2 stands apart. To call it ghostly isn't just poetic, it is almost literal. If you were to gaze at DF2 through an ordinary telescope, you would struggle to see anything at all. The stars are not packed tightly into luminous arms or clustered in a bright core. Instead, they are sprinkled sparsely across an area comparable in size to the Milky Way, tens of thousands of light-years wide, but with only a tiny fraction of the Milky Way's stellar population. Where the Milky Way contains perhaps 200 to 400 billion stars, DF2 holds only a few hundred million. Spread across such a vast expanse, those stars become little more than faint points of light scattered across a nearly invisible canvas. This diffuse arrangement gives DF2 an almost transparent quality. Unlike most galaxies, which block the light of objects behind them, DF2 allows us to see straight through it. When astronomers photograph it, background galaxies shine clearly through its tenuous structure. It is as if DF2 is more absence than presence, a skeletal remnant of what a galaxy should be. Van Dockum himself described it as a galaxy you can see through, a remark that instantly captured the imagination of the scientific community and the public alike. The effect is even more unsettling when compared side by side with the Milky Way. Imagine spreading out all the stars of our galaxy over the same area, but reducing their number by a factor of hundreds. The Milky Way's dense disk and glowing arms would dissolve into a faint haze. That's DF2, a galactic phantom that occupies the space of a giant galaxy but shines like a dwarf. Its surface brightness is so low that without specialized instruments like the Dragonfly telephoto array, it would have remained invisible. This ultra-diffuse nature also feeds directly into its mystery. Galaxies typically owe their structure and coherence to dark matter, which exerts the gravitational pull needed to bind stars together. Without that glue, stars would drift apart and the galaxy would disintegrate. Yet DF2, despite appearing like a fragile mist, somehow persists. Its ghostly form whispers a contradiction. It shouldn't be there at all. The galaxy's faintness also complicates the job of astronomers trying to study it. Measuring distances, star velocities, and even stellar populations becomes extremely challenging when there's so little light to work with. Yet the faint glow is also what makes DF2 so compelling. It embodies the sense of fragility, like a relic of something ancient that has survived against all odds. To look at DF2 is to confront the fragility of structure itself on a galactic scale, a reminder that not all galaxies blaze with glory. Some exist in shadows, dimly lit but impossibly real. In photographs captured with the Hubble Space Telescope, DF2 appears as a dim scattering of pale light, punctuated by a handful of star clusters that stand out like jewels against an otherwise washed-out backdrop. These clusters are brighter than the galaxy's field stars and seem almost oversized, like ornaments hanging on a barely there framework. The rest of the galaxy is so tenuous that it blends into the cosmic background, barely distinguishable unless you know exactly where to look. This visual emptiness is what makes the galaxy so chilling to contemplate. When astronomers describe it as ghostly, they aren't exaggerating. NGC 1052-DF2 looks like the spectre of a galaxy, a hollow framework of starlight stripped of substance. It feels less like a galactic structure and more like the afterimage of one, as though the cosmos is showing us what happens when the essential ingredients of galaxies, gas, stars, and dark matter, are tampered with or removed. Its appearance is not only a curiosity, but also a clue. The diffuse skeletal structure suggests that something drastic has shaped its evolution. Was it torn apart by gravitational interactions with its massive neighbour, NGC 1052? Was it born this way, a failed galaxy that never managed to accumulate gas and dark matter properly? Or is it an artifact of some cosmic process we don't yet understand? Whatever the case, the ghostly appearance of DF2 is not merely aesthetic. It is a symptom of its deeper strangeness, a signpost pointing to mysteries hidden within its faint starlight. To astronomers, studying DF2 is like trying to study a shadow made of stars. Its diffuse, transparent structure challenges not just instruments, but also our imagination, forcing us to think of galaxies not as luminous beacons, but as fragile phantoms that can exist at the margins of possibility. The greatest shock about NGC 1052-DF2 was not simply how it looked, but what it lacked. As astronomers probed deeper into its structure, they came face to face with an absence so profound that it shook their understanding of galaxies themselves. That missing ingredient was dark matter, the mysterious, unseen substance thought to dominate the mass of the universe and act as the invisible glue that binds galaxies together. According to decades of theory and observation, dark matter is not optional for galaxies. It is the very foundation upon which they are built. Yet in DF2, it was almost nowhere to be found. To grasp how startling this is, it's important to understand why dark matter has become such a central pillar of cosmology. Observations of galaxies over the past century have consistently shown that their visible matter, the stars, gas, and dust, cannot account for the gravitational forces keeping them intact. Stars at the edges of galaxies move much faster than they should, if only visible matter were present. Without an extra, invisible source of gravity, these galaxies should simply fly apart. The solution proposed was dark matter, an unseen form of matter that exerts gravitational pull but does not emit or absorb light. By adding this invisible mass into the equations, the motions of stars and galaxies suddenly made sense. In fact, dark matter is thought to outnumber normal matter by a factor of about 5-1. With that in mind, the discovery of DF2 presented a jarring contradiction. Peter van Dokkum and his team expected to find that this ultra-diffuse galaxy, like all others studied before, would be dominated by dark matter. Instead, their careful measurements of the velocities of globular clusters orbiting within DF2 revealed something extraordinary. The total mass of the galaxy matched almost perfectly with the mass of its stars alone. There was no need to invoke dark matter to explain the data. In essence, DF2 appeared to be a galaxy without glue, a sprawling collection of stars held together only by their own gravity, with no hidden reservoir of dark matter providing extra stability. This was like discovering a skyscraper standing tall with no steel beams inside, or a solar system with planets orbiting perfectly without a central star. For astronomers, it was not just surprising, it was deeply unsettling. If dark matter really is the cornerstone of galaxy formation, how could a galaxy of DF2's size and scale exist without it? Was this galaxy a freak accident, a 1 in a billion outlier, or was it a sign that our entire model of the universe might be incomplete? The absence of dark matter in DF2 also struck at the heart of a common assumption in astrophysics, that galaxies and dark matter are inseparably linked. The prevailing picture imagines galaxies forming inside large halos of dark matter, with that halo providing the gravitational framework necessary for gas to collapse and form stars. Without such a halo, gas should never have condensed enough to spark star formation in the first place. In other words, without dark matter, galaxies shouldn't exist. Yet here was DF2, calmly floating in space, contradicting this basic idea. Some astronomers initially suggested that perhaps the data were wrong. Maybe DF2 wasn't as far away as van Dokkum's team thought. If the galaxy were closer, its stars and clusters would be intrinsically fainter and smaller than assumed, and the calculations for its mass could change drastically. Others wondered if the velocities of the star clusters had been measured inaccurately, or if the faint, ghostly appearance of the galaxy had somehow tricked the instruments. But repeated checks, careful recalculations, and eventually independent confirmations by the Hubble Space Telescope only strengthened the conclusion. DF2 really did lack dark matter, at least to an extent never before seen. This missing ingredient was more than just a curiosity. It was a challenge to one of the most robust frameworks in physics. Dark matter has never been directly detected in a laboratory, but its gravitational fingerprints are everywhere in the cosmos. To find a galaxy where those fingerprints seem to vanish was both exhilarating and alarming. If dark matter is truly universal, DF2 should not exist. And if DF2 does exist, then maybe our understanding of dark matter is flawed. Or, more provocatively, maybe dark matter itself does not exist in the way we think. For the scientific community, this created a paradox. Either DF2 was an exotic anomaly that could be explained away by special circumstances, or it was a crack in the foundation of cosmology, hinting at a deeper truth about the universe. In both cases, the absence of dark matter in DF2 became not just a footnote in astronomy, but a headline, a cosmic riddle that forced experts to re-examine assumptions they had long taken for granted. The missing ingredient turned DF2 from a faint, overlooked smear of stars into a cosmic enigma. It wasn't just its ghostly transparency that made it strange, it was what wasn't there, the silence of the invisible matter that should have been its skeleton. By stripping away dark matter, DF2 revealed a universe that is stranger and more fragile than we imagined. A reminder that even the laws we consider universal may have exceptions lurking in the shadows of the cosmos. Dark matter has long been considered one of the most essential yet elusive components of the universe. Although it cannot be seen, touched, or detected directly with current instruments, its influence is felt everywhere, shaping the cosmos on scales both vast and minute. Its importance becomes especially clear when we consider galaxy formation and stability. Galaxies are not simply random collections of stars. They are massive, gravitationally bound systems that require an enormous amount of mass to remain coherent over billions of years. Without dark matter, galaxies as we know them would likely not exist at all. In the traditional picture of galaxy formation, the universe began with tiny fluctuations in the density of matter shortly after the Big Bang. Normal matter, hydrogen, helium, and trace amounts of heavier elements, was subject to radiation pressure and thermal energy, making it difficult for gas to collapse and condense into dense structures on its own. Dark matter, however, does not interact with light or radiation, so it could start clumping together long before normal matter could. These clumps of dark matter formed the gravitational scaffolding around which gas could accumulate, eventually cooling, collapsing, and forming stars. Essentially, dark matter acts as a cosmic blueprint, providing the invisible gravitational framework necessary for the luminous components of galaxies to exist. Once a galaxy forms, dark matter continues to play a crucial role in maintaining its stability. Stars orbit around the galaxy's center under the influence of gravity. In many galaxies, the observed speed of stars, particularly those at the outer edges, is far too high to be accounted for by the gravity of visible matter alone. Without an additional mass component, these stars would fly away and the galaxy would dissipate. Dark matter, forming a massive halo around the galaxy, exerts the necessary gravitational pull to keep stars bound in place. This invisible halo also ensures that galaxies remain resilient to external gravitational disturbances, such as interactions with other galaxies or tidal forces within clusters. In short, dark matter is not merely helpful, It is indispensable for the very existence and longevity of galaxies. The amount of dark matter within a galaxy is typically staggering. In spiral galaxies like the Milky Way, dark matter can outweigh visible matter by a factor of 5 to 10. Even dwarf galaxies, which contain far fewer stars, are dominated by dark matter, sometimes by factors exceeding 100. Observational evidence from rotational curves, gravitational lensing, and cosmic microwave background studies consistently supports this framework. Dark matter provides the gravitational glue that holds galaxies together, the invisible skeleton around which luminous matter organizes, and the stabilizing force that allows galaxies to survive for billions of years without collapsing or disintegrating. Without dark matter, the process of galaxy formation would be radically different. Gas clouds would struggle to collapse under their own gravity, star formation would be inefficient, and any stars that did form would be far more vulnerable to gravitational disruption. A galaxy lacking dark matter would be like a building made entirely of glass and air. It might hold together momentarily, but any perturbation could shatter it. The very existence of galaxies in our universe, from the smallest dwarf to the largest spiral, seems to hinge on this unseen component. It is both a prerequisite for formation and a guarantee of stability, ensuring that galaxies not only appear but persist across cosmic time. This is why the discovery of NGC 1052-DF2 is so extraordinary. Here is a galaxy whose mass and stellar motions suggest that dark matter is either minimal or entirely absent. DF2 seems to exist and maintain its structure without the gravitational backbone that dark matter typically provides. If dark matter is essential for the formation and stability of galaxies, then a galaxy like DF2 presents a profound paradox. It is defying the very principle that explains the existence of all other galaxies observed in the universe. Its apparent lack of dark matter challenges astronomers to reconsider how galaxies can form and survive, and whether our models of the cosmos need revision. Moreover, the implications go beyond a single galaxy. If DF2 is not an anomaly, but part of a class of galaxies that can exist without dark matter, it could reshape our understanding of the universe on a fundamental level. Cosmologists rely on the assumption that dark matter is universal, affecting everything from the behavior of individual stars to the expansion of the universe itself. The presence of a galaxy that thrives without it is akin to finding a bird that flies without wings. Entirely possible, yet utterly baffling. DF2 forces scientists to confront questions they never expected to ask. Can galaxies form without dark matter at all? Are there alternative mechanisms capable of holding stars together? Could dark matter itself be more complex, or perhaps only one part of a bigger, more mysterious cosmic puzzle? NGC 1052-DF2 presents a cosmic paradox so striking that astronomers often describe it as a galaxy without glue. In every other galaxy we have studied, dark matter functions as an invisible framework, holding stars together through its gravitational pull. It is the scaffold that prevents a galaxy from drifting apart, the unseen hand keeping stars bound in coherent orbits over billions of years. DF2, however, appears to defy this fundamental principle, maintaining its structure without the stabilizing influence of dark matter. From a theoretical standpoint, a galaxy lacking this essential glue should have torn itself apart long ago, scattering its stars across intergalactic space. Yet here it is, remarkably intact, an ultra-diffuse system floating serenely in the void. The paradox becomes even more acute when we examine the dynamics of the stars and globular clusters within DF2. In typical galaxies, stars at the periphery move at speeds that require a massive halo of dark matter to keep them gravitationally bound. Without that halo, stars would exceed the escape velocity of the system, and the galaxy would dissipate in a few million years, a mere blink in cosmic terms. DF2, however, displays stellar velocities entirely consistent with the mass of its stars alone. There is no hidden reservoir of dark matter providing extra gravitational cohesion. By all conventional measures, it should have disintegrated billions of years ago. The term galaxy without glue is particularly apt because it underscores the fragility implied by DF2's structure. Its stars are spread out so diffusely that one could almost see through the galaxy, making it appear like a celestial ghost. In most galaxies, the dense stellar population, combined with the gravitational pull of dark matter, keeps stars tightly bound in a resilient system. DF2's ultra-diffuse nature, combined with the apparent absence of dark matter, should render it highly unstable. Tidal interactions with nearby galaxies, perturbations from passing cosmic objects, or even internal gravitational instabilities should have caused the galaxy to collapse or scatter long ago. Yet DF2 persists, a phantom of stability against all odds. Some theories attempt to reconcile this paradox by suggesting that DF2 might be relatively young, or that it is in a temporary, fleeting state of equilibrium. Perhaps we are witnessing the galaxy at a rare moment in its evolution, just before it finally succumbs to the inevitable pull of cosmic forces. But measurements of its stellar populations indicate that DF2 contains ancient stars, comparable in age to those in more conventional galaxies. This implies that it has survived for billions of years without the stabilizing presence of dark matter, deepening the enigma. Another aspect of this paradox involves the galaxy's interactions with its environment. DF2 exists in the vicinity of the massive elliptical galaxy NGC 1052, a gravitational powerhouse capable of influencing neighboring galaxies. One might speculate that tidal interactions or past mergers could have stripped DF2 of dark matter, leaving behind a fragile stellar skeleton. Even if this were true, the remaining stars would still be at risk of dispersal, and the galaxy's survival would require an extraordinarily delicate balance of forces. The fact that it has remained coherent despite these conditions emphasizes just how puzzling its existence is. Astronomers have also compared DF2 with theoretical simulations of galaxy formation. Most simulations predict that galaxies without dark matter either fail to form stars efficiently or collapse entirely under the influence of their own gravitational instabilities. Yet, DF2 does not conform to these predictions. It has formed stars, developed bright globular clusters, and maintained a recognizable, though ultra-diffuse, galactic shape. In essence, it is a living contradiction, a galaxy that defies the physical laws we rely on to explain the cosmos. The galaxy without glue concept also sparks broader questions about the limits of our understanding. If a galaxy like DF2 can exist, then perhaps dark matter is not as universally indispensable as previously thought. Or perhaps there are alternative mechanisms at play that can stabilize galaxies in the absence of dark matter. Could modified gravitational dynamics, unknown forms of matter, or unique environmental factors be compensating for what is missing? Each hypothesis presents its own challenges, and none can fully explain the enduring stability of DF2. Ultimately, the paradox of DF2 lies not just in its existence, but in its apparent resilience. This galaxy, a faint and ghostly assemblage of stars, has persisted without the cosmic glue that is considered essential for galactic survival. It challenges assumptions that astronomers have treated as near axiomatic for decades. DF2 is a living counterexample to conventional wisdom, a striking reminder that the universe does not always conform to our expectations. Its very existence forces scientists to ask, Can galaxies survive without dark matter, or is DF2 an extraordinary exception in a universe that largely obeys the rules we think we understand? One of the most confounding aspects of NGC 1052-DF2 is its sheer scale compared to its stellar content, a discrepancy that has been dubbed the size versus mass mystery. When astronomers measured its dimensions, they found that DF2 stretches across roughly 60,000 light-years, placing it in the same size category as galaxies like the Milky Way. At first glance, such a scale suggests a massive galaxy. After all, most galaxies of this size harbor hundreds of billions of stars, with dense cores and sprawling spiral arms that dominate their neighborhoods. Yet DF2 is radically different. Its total stellar mass is incredibly low, roughly 1/100th that of the Milky Way, meaning that for its enormous size, it contains a tiny fraction of the stars one would expect. This combination of vast physical dimensions and sparse stellar population immediately raises profound questions about how it formed and evolved. The implications of this disparity are staggering. In a conventional galaxy, mass is closely correlated with size. Larger galaxies typically have more stars, more gas, and more dark matter. This makes intuitive sense because gravity, the key force shaping galaxies, draws in matter, concentrating it over time. DF2 breaks this correlation spectacularly. Its diffuse, ultra-extended structure means that stars are spread far apart, creating an incredibly low stellar density. For comparison, if the Milky Way were stretched into the same diffuse configuration as DF2, it would be a faint haze, almost invisible, with stars so sparsely distributed that the galaxy's gravitational cohesion might be compromised. DF2 appears to function as a galaxy, yet it seems to defy the scaling laws that apply to nearly every other galaxy we know. Adding to the mystery is the way DF2's globular clusters behave. Unlike the faint, dim clusters typically found in dwarf galaxies, DF2 hosts unusually massive and luminous clusters. These clusters are spread across the galaxy's enormous diameter, yet the overall stellar mass remains exceptionally low. The combination of a Milky Way-sized radius with just a few 100 million stars is almost unprecedented. While the galaxy occupies the same physical footprint as a giant spiral, the sheer lack of stars makes it extremely faint, contributing to its ghostly, almost transparent appearance. Its stars are so spread out that astronomers can see background galaxies shining through it, emphasizing the extreme sparsity of its stellar content. This size-to-mass paradox also has profound implications for galaxy formation theories. In standard models, the amount of gas available during the galaxy's formation should correlate with the eventual number of stars and the size of the stellar disk. DF2 suggests that this relationship can break down under certain conditions. Its formation history must have involved either a mechanism that spread its stars unusually thin, or a process that removed most of its stars or gas after formation. Theories have been proposed, ranging from tidal interactions with neighboring massive galaxies to extreme feedback processes that expelled gas before it could form stars. Yet none of these explanations fully account for the extraordinary combination of DF2's size and extremely low stellar mass. Another layer of the mystery comes from DF2's stellar velocity measurements, which provide insights into its mass distribution. Even though the galaxy spans tens of thousands of light-years, the stars and globular clusters move slowly enough to suggest that there is very little unseen mass holding them together. In most galaxies of this size, the stellar velocities would be dominated by the gravitational influence of dark matter, resulting in faster motions, especially in the outer regions. DF2 defies this expectation. Its star's movements are consistent with the mass contributed solely by its visible stars, reinforcing the idea that it is not only underpopulated but also virtually devoid of dark matter. This reinforces the size versus mass discrepancy. The galaxy is physically large yet extremely lightweight. The size versus mass mystery becomes even more perplexing when we consider DF2 in the context of other ultra-diffuse galaxies, UDGs. UDGs are already unusual. They tend to have low stellar densities and faint appearances, but DF2 is an outlier even among them. Most UDGs still show evidence of significant dark matter halos that provide stability, despite their low stellar content. DF2, in contrast, manages to maintain its structure without relying on dark matter, making its large, sparse size even more enigmatic. The galaxy seems to occupy a previously unrecognized niche, a system that is physically extensive, almost spectral in appearance, yet gravitationally anomalous. Astronomers have speculated that DF2 might be a failed galaxy of sorts, a system that started forming like a normal galaxy but somehow lost the bulk of its mass before completing the process. Perhaps during its early history, supernova-driven winds expelled gas, preventing further star formation. Or maybe gravitational interactions with the nearby massive galaxy NGC 1052 stripped it of material, leaving a ghostly skeleton behind. Even if either of these scenarios is true, the size and mass discrepancy remains difficult to reconcile. No known mechanisms fully explain how a galaxy could maintain such a large radius while retaining only a fraction of the expected stars. The paradox also has implications for our understanding of dark matter. The general assumption is that galaxies like DF2 require a dark matter halo to remain stable over cosmic time. But in DF2, the size is enormous while the mass is minuscule, and yet the galaxy survives. This challenges the conventional notion that dark matter and baryonic visible matter scale together in a predictable way. DF2's existence hints that either some unknown mechanism is compensating for the missing mass, or that our understanding of how dark matter interacts with stars in ultra-diffuse environments is incomplete. DF2's unusual size-to-mass ratio also raises intriguing questions about how we classify galaxies. Traditionally, galaxies are categorized based on mass, luminosity, and morphology. DF2 doesn't fit neatly into any category. It is too large to be a dwarf galaxy, yet too low in stellar content to resemble a normal spiral or elliptical. Its diffuse nature and enormous size make it appear ghost-like, yet its structural integrity suggests a level of stability unexpected for a system with so little mass. It is a galaxy that refuses to conform, a celestial object that simultaneously occupies the space of giants while carrying the weight of dwarfs. One of the most visually striking and conceptually baffling features of NGC 1052-DF2 is its transparency, a direct consequence of its ultra-diffuse structure. Unlike the dense, bright galaxies that dominate the night sky, DF2 is so sparsely populated with stars that its light is extremely faint, and the gaps between individual stars are enormous on a cosmic scale. This allows astronomers, and even the most sophisticated telescopes, to see straight through it to the distant galaxies lying behind it. The effect is almost surreal. A galaxy that should act as an opaque island in space instead functions like a spectral veil, a ghostly smudge through which the universe beyond can be glimpsed. In images captured by instruments such as the Hubble Space Telescope, this transparency is clearly visible, giving DF2 an ethereal, otherworldly appearance. The transparency of DF2 is not merely a curiosity, it reflects a profound peculiarity in the distribution of its stellar mass. In a typical galaxy of similar size, stars are densely clustered, forming a bright core and prominent spiral arms or elliptical bulge. This concentration of light effectively shields the background, creating a dense barrier that blocks or distorts the light from more distant objects. DF2, however, has an incredibly low stellar density. Its stars are scattered across tens of thousands of light-years, leaving vast regions of nearly empty space between them. This gives the galaxy a diffuse luminosity so faint that when astronomers image it, background galaxies are visible through its structure, as if the galaxy is more of a skeleton than a solid object. This transparency also underscores the fragile nature of DF2. In most galaxies, the gravitational pull of dark matter, combined with the collective gravity of stars, ensures that stellar populations remain bound together over billions of years. DF2's stars, however, are so spread out that the galaxy should, by conventional understanding, be extremely vulnerable to tidal forces and other gravitational disturbances. Its ultra-low surface brightness, combined with its lack of dark matter, creates a system where stars are isolated, yet somehow still maintaining a tenuous cohesion. The result is a ghostly galaxy that exists in delicate balance, neither as bright nor as gravitationally robust as typical galaxies of comparable size. The transparent nature of DF2 is particularly evident when astronomers examine its globular clusters. These clusters are massive, bright, and stand out sharply against the faint stellar background. When observed through telescopes, they appear as luminous beacons scattered within the diffuse field of the galaxy. Between these clusters, however, there is almost nothing. Photons from galaxies billions of light-years away pass unobstructed through these gaps, allowing astronomers to capture both DF2 and the distant cosmic landscape behind it in the same frame. This effect is unlike what we observe in most galaxies, where dense stellar populations block background light, demonstrating just how sparse and unusual DF2 truly is. Transparency also contributes to the eerie, almost spectral impression that DF2 gives. Astronomers describe it as a galactic ghost, a system whose presence is defined less by the density of its stars than by the space between them. While most galaxies announce themselves with bright cores and glowing arms, DF2 seems to whisper its existence, a dim and ephemeral presence that reveals the void as much as it does the galaxy itself. The visual effect is striking and haunting. Looking at DF2 is like looking at a shadow of a galaxy rather than a conventional stellar system. From a scientific perspective, this transparency is also critical for studying the galaxy's properties. Because its stars are so sparse, astronomers can measure individual stars and globular clusters more precisely, minimizing confusion from overlapping light sources. However, the faintness also presents observational challenges. Detecting and confirming the properties of DF2 requires extremely sensitive instruments, long exposure times, and specialized data analysis techniques. The very property that makes DF2 fascinating, its transparency, is the same property that makes it exceptionally difficult to study in detail. The ghostly transparency of DF2 further reinforces the paradox of its existence. A galaxy that is both so diffuse and lacking dark matter should, by all conventional astrophysical rules, have long since dispersed into the intergalactic medium. The fact that its stars remain loosely bound and coherent, while still allowing background galaxies to shine through, highlights the fragile yet stable equilibrium DF2 inhabits. It is a galaxy at the extreme edge of physical possibility, challenging astronomers to reconcile its spectral appearance with its gravitational persistence. Additionally, the transparency offers insights into galaxy evolution in ultra-diffuse systems. DF2 may represent a case study in how a galaxy can form or survive with minimal stellar mass and negligible dark matter. Its visible sparsity suggests that some ultra-diffuse galaxies could evolve without ever accumulating dense stellar populations, potentially explaining the existence of other ghostly galaxies observed in deep sky surveys. DF2's ability to maintain coherence while being so transparent may indicate previously unknown processes in galaxy formation, perhaps tied to tidal stripping, early feedback from supernovae, or unconventional gravitational effects. One of the most perplexing features of NGC 1052-DF2 is the population of globular clusters it hosts, clusters of stars that are unusually bright, massive, and large for a galaxy of its type. Globular clusters are dense groupings of ancient stars, often found orbiting the halos of galaxies, and they serve as cosmic fossils, preserving the history of stellar formation. Most galaxies of DF2's size, or even far smaller, have globular clusters that are relatively faint and modest in mass, typically ranging from tens of thousands to a few 100,000 solar masses. DF2, however, defies this expectation. Its globular clusters are astonishingly luminous and massive, with some exceeding 1 million solar masses, placing them at the extreme end of known globular cluster properties. These clusters are not only massive, but also remarkably large in size, stretching over distances that are unusual for such systems. In typical galaxies, the clusters are tightly bound and compact, containing a high density of stars in a relatively small region of space. In DF2, however, the clusters appear more spread out and diffuse, yet they retain their structural integrity. Their brightness and size make them stand out starkly against the ultra-diffuse backdrop of the galaxy, almost like oversized jewels scattered across a faint cosmic veil. They are visually striking and scientifically confounding. Their very existence raises questions about how they could have formed and survived in a galaxy with almost no dark matter. The number of globular clusters in DF2 is also extraordinary. While dwarf galaxies and ultra-diffuse galaxies typically host only a handful of clusters, DF2 has about 10 to 12 massive clusters orbiting within it. Given the galaxy's low total stellar mass, this is an unusually high proportion. In a galaxy like DF2, which is about the size of the Milky Way, but contains only a tiny fraction of its stars, the presence of such a rich cluster population seems improbable. Conventional theories of star formation suggest that forming these massive clusters requires conditions typically associated with more massive and gravitationally robust galaxies, especially environments dominated by dark matter. In DF2, the clusters seem almost too big and too numerous to be supported by the galaxy's meager mass. The globular clusters of DF2 also exhibit orbital behavior that deepens the mystery. Measurements of their velocities indicate that they are moving under the influence of the visible stellar mass alone, with no significant dark matter halo to stabilize their orbits. In standard galactic dynamics, such massive clusters would normally be tightly bound by a combination of the galaxy's stars and dark matter. Without that extra gravitational support, one would expect these clusters to have been disrupted over cosmic time, or at least to have been ejected from the galaxy. Yet in DF2, the clusters remain in stable orbits, suggesting either an unknown stabilizing mechanism or a unique formation history that allowed them to persist despite the lack of dark matter. Another fascinating aspect is the relationship between the clusters and the galaxy itself. The clusters are proportionally much more significant relative to DF2's total stellar mass than in most galaxies. In typical systems, the mass contained in globular clusters is a small fraction of the total galactic mass. In DF2, however, The clusters make up a substantial portion of the galaxy's total stellar content, further highlighting the peculiar distribution of matter within this galaxy. This anomaly raises questions about whether DF2's clusters formed alongside the galaxy's stars, or if they were somehow assembled under different conditions, perhaps even preceding the formation of the diffuse stellar population that dominates DF2. The unusual globular clusters also challenge existing models of galaxy evolution. In standard cosmological simulations, the formation of such massive clusters is often linked to the presence of dark matter halos, which provide the gravitational scaffolding necessary for dense star formation. DF2's clusters exist in a galaxy where dark matter appears to be almost entirely absent, implying that either massive clusters can form in ways that do not require a dark matter halo, or that DF2 experienced a dramatic event, such as tidal stripping from a neighboring galaxy, that removed its dark matter after cluster formation. Either scenario is extraordinary and suggests that the processes governing cluster formation and survival may be more diverse than previously understood. The cluster's luminosity also offers clues about DF2's stellar population and age. Spectroscopic studies indicate that the clusters are ancient, with ages exceeding 9 to 10 billion years, making them nearly as old as the universe itself. Their brightness is therefore not due to youthful stars, but to the sheer mass of the clusters, reinforcing the idea that DF2 has retained these dense stellar systems for nearly the entire history of the cosmos, despite its extremely low overall mass. This stability is difficult to reconcile with the absence of dark matter, highlighting yet again how DF2 appears to operate outside the normal rules of galaxy formation and evolution. In essence, these globular clusters are galaxies within a galaxy, unusually massive, luminous and resilient, orbiting within a ghostly, diffuse structure that seems almost incapable of holding them. Their existence compounds the mystery of DF2. Not only is it a galaxy without dark matter, but it also hosts star clusters that, under conventional understanding, should not exist in such an environment. These clusters are both a visual and theoretical anomaly, providing astronomers with a unique laboratory to study star formation, cluster dynamics, and the interplay between visible matter and dark matter, or the absence of it. When the initial findings on NGC 1052-DF2 were published, the astronomical community reacted with a combination of astonishment, skepticism, and outright disbelief. The claim that a galaxy of DF2's size could exist virtually devoid of dark matter was almost unthinkable. For decades, the standard model of cosmology, supported by both theoretical predictions and observational evidence, assumed that dark matter was ubiquitous in galaxies, serving as the fundamental scaffold around which stars and gas coalesced. To suggest a galaxy that defied this principle was tantamount to challenging a cornerstone of modern astrophysics. For many researchers, the news sent a metaphorical shockwave rippling through the field, shaking long-held assumptions and prompting urgent calls for verification. In the early days following the 2018 announcement by Peter van Dokkum and his team, much of the discussion focused on the implausibility of the findings. Leading astronomers expressed caution, emphasizing the extraordinary nature of the claim. Some suggested that the results could be explained by errors in distance measurements. If DF2 were closer than originally thought, its observed size and mass would be recalibrated, potentially removing the apparent paradox of missing dark matter. Others speculated that the velocity measurements of its globular clusters might be misleading. Measuring the motion of stars and clusters in such faint and diffuse galaxies is notoriously difficult, requiring careful calibration and correction for observational biases. Skeptics wondered whether instrumental limitations or statistical anomalies, might have produced an artificial signal suggesting the absence of dark matter. The announcement also triggered intense scrutiny of the methodology. DF2's discovery relied on observations from the Dragonfly telephoto array, an instrument specifically designed to detect low-surface brightness galaxies. While Dragonfly's capabilities are revolutionary, the uniqueness of DF2's properties prompted astronomers to question whether subtle observational effects could have skewed the results. Could the ultra-diffuse nature of the galaxy have masked underlying dark matter, or had assumptions about stellar mass-to-light ratios been misapplied? Peer reviewers and astronomers alike debated these possibilities, reflecting the high stakes of verifying such a paradigm-challenging discovery. Beyond methodological skepticism, DF2's announcement also sparked theoretical debates. Cosmologists asked, if a galaxy can exist without dark matter, does this undermine the standard lambda cold dark matter model of cosmology? The model predicts that dark matter halos are essential for galaxy formation, and their absence in DF2 seemed to contradict this principle. Some theorists argued that the galaxy might represent a rare, extreme outlier, a fluke of nature that does not threaten the overall framework. Others contended that even a single confirmed case of a galaxy without dark matter could indicate gaps in our understanding of cosmic structure formation. The early discourse was marked by intense excitement, cautious skepticism, and a sense of urgency to confirm the discovery. Interestingly, the shockwave extended beyond purely scientific circles. The idea of a galaxy defying the rules of the universe captured public imagination, with media outlets sensationalizing the finding as a cosmic anomaly or interstellar paradox. Headlines emphasized the notion of a galaxy without glue, or breaking the laws of physics, amplifying curiosity and debate. While popular coverage often simplified or dramatized the science, the excitement reflected a genuine sense of wonder within the community. Here was a galaxy that challenged fundamental assumptions and invited scientists to rethink what is possible in the cosmos. Amid this initial wave of disbelief, some astronomers proposed alternative scenarios to reconcile the data with conventional models. A common suggestion was that the galaxy might be oriented in such a way that we underestimated its mass. Others hypothesized that DF2 could have undergone unusual evolutionary processes, such as tidal stripping by nearby massive galaxies, which removed both dark matter and stars, leaving behind a diffuse remnant. While these ideas offered potential explanations, none were fully satisfactory, and the paradox remained unresolved. The very fact that multiple hypotheses had to be proposed underscored the galaxy's extraordinary nature. DF2 did not fit neatly into any known category. Despite initial skepticism, Van Dokkum and his team stood by their analysis, emphasizing the robustness of their measurements and the careful calibration of their data. They encouraged independent verification using other instruments, recognizing that such a groundbreaking claim demanded confirmation. This transparency helped drive a flurry of follow-up studies, both observational and theoretical, aimed at understanding DF2's properties, dynamics, and origins. Over time, additional measurements and analyses began to support the original conclusion. DF2 is indeed a real galaxy, extraordinarily diffuse and almost entirely lacking dark matter. Following the initial shock and skepticism surrounding the discovery of NGC 1052-DF2, astronomers and theorists began exploring alternative explanations to account for its seemingly impossible properties. Given that the galaxy appeared to lack dark matter, a foundational pillar of cosmology, scientists were cautious, considering the possibility that the anomaly might be a product of observational or methodological errors rather than a genuine cosmic paradox. These alternative theories ranged from subtle measurement inaccuracies to more complex scenarios involving misinterpretation of the galaxy's properties. One of the earliest and most discussed possibilities involved errors in distance measurements. Determining the distance to a galaxy is critical because its apparent size, brightness, and derived mass all depend on how far away it is. If DF2 were closer than originally estimated, its physical dimensions would shrink, and its total stellar mass would be recalculated upwards, potentially bringing it more in line with expectations for a galaxy of its apparent size. Distance measurements often rely on standard candles, such as globular clusters or variable stars, whose intrinsic brightness is well understood. Any misestimation in the brightness of these objects could skew distance calculations. Some astronomers suggested that if the galaxy were closer by even a factor of 2, the perceived lack of dark matter might be an illusion, resulting from an underestimation of the gravitational contribution of its stars. Another avenue considered was measurement errors in the stellar velocities used to infer the galaxy's mass. DF2's mass was primarily determined by observing the motion of its globular clusters, whose velocities indicate the gravitational pull exerted by the galaxy as a whole. However, measuring these velocities in such faint, distant systems is inherently challenging. The spectral lines of stars or clusters can be weak, noisy, or affected by instrumental limitations. If the velocities were slightly underestimated, the inferred total mass of DF2 could appear lower than it actually is. Some researchers argued that even small observational errors could exaggerate the apparent discrepancy between the galaxy's visible matter and the expected dark matter halo. Beyond technical errors, some astronomers proposed that DF2's unusual properties might be a result of observational illusions or projection effects. For example, the galaxy could be elongated along our line of sight, making it appear larger and more diffuse than it actually is. Alternatively, its stars might be concentrated in a certain plane or orientation, leading to underestimation of the galaxy's mass if we only observed certain components. In these cases, the galaxy might still contain dark matter, but its distribution could be unusual or oriented in a way that deceives our instruments. Such explanations were appealing because they could preserve conventional cosmological models without invoking a fundamentally new type of galaxy. Some theorists also explored the possibility of statistical anomalies. DF2 is an ultra-diffuse galaxy, a rare class of galaxies that are faint and spread out. The extreme properties of DF2 might represent a statistical outlier, an unusual but not impossible configuration within the range of galaxy formation processes. In this view, the apparent lack of dark matter could be a natural, if exceedingly rare, consequence of the galaxy's evolutionary history, rather than a challenge to fundamental physics. This theory suggested that while DF2 is remarkable, it might not require a radical revision of dark matter models, but rather a deeper understanding of the diversity of galactic systems. Yet another line of alternative reasoning focused on the role of globular clusters as tracers. Since DF2's mass estimates were based on the motions of its globular clusters, some suggested that the clusters themselves might not be fully representative of the galaxy's total gravitational potential. Perhaps they occupy orbits that happen to be unusually slow or aligned in a manner that underestimates the total mass. If this were the case, DF2 might still contain a significant amount of dark matter, but our observational proxies, the globular clusters, gave a misleading picture. This theory relied on the assumption that the sampling of clusters could skew the interpretation, a reasonable concern given the small number of clusters observed. Despite these alternative theories, each faced significant challenges when tested against observational data. Distance recalculations, for example, were limited by the precision of standard candle measurements, and repeated observations with the Hubble Space Telescope confirmed that DF2 is indeed at the originally reported distance, approximately 65 million light-years away. Similarly, refined velocity measurements continued to indicate a stellar mass consistent with the observed motions, leaving little room for hidden dark matter. Observational illusions or projection effects could not fully reconcile the size, mass, and dynamics of the galaxy, particularly given the independent conformation of its globular cluster properties and their unusually high velocities relative to the visible stellar mass. In the face of these challenges, astronomers realized that while alternative explanations were valuable to explore, the data increasingly pointed toward the extraordinary reality of DF2 as a galaxy with minimal dark matter. These initial alternative theories served a crucial role, however. They pushed researchers to scrutinize every detail of the discovery, refine their instruments and methods, and ensure that the conclusion was robust. In doing so, DF2 became one of the most carefully examined galaxies in recent decades, with repeated observations and analyses confirming that it is not simply an artifact of measurement or illusion, but a real, tangible system defying conventional expectations. The extraordinary claims about NGC 1052-DF2, its ultra-diffuse nature, its ghostly transparency, and most provocatively, its apparent lack of dark matter, prompted astronomers to seek independent confirmation using the most powerful observational tools available. Chief among these was the Hubble Space Telescope, HST, whose unparalleled sensitivity and resolution allow it to detect faint stars and measure distances with remarkable precision. Follow-up observations with Hubble were critical not only to verify the existence of DF2, but also to confirm the startling conclusion that this galaxy is missing virtually all of the dark matter that, according to conventional theory, should dominate its mass. Hubble's imaging of DF2 focused first on resolving individual stars and globular clusters within the galaxy. The Dragonfly telephoto array, which initially discovered DF2, was optimized for detecting ultra-low surface brightness structures, but could not provide the precise measurements needed to confirm stellar distances or detailed dynamics. Hubble's observations allowed astronomers to analyze the brightness, color, and spatial distribution of stars with exquisite detail. By applying techniques such as surface brightness fluctuations, SBF, and analyzing the luminosity function of resolved stars, astronomers could accurately estimate the distance to DF2. These measurements confirmed that DF2 lies roughly 65 million light-years away, consistent with the original estimates by Van Dokkum and his team, effectively ruling out distance miscalculations as a source of the anomaly. Equally important, Hubble observations enabled precise measurements of the globular cluster's properties, their brightness, size, and orbital velocities. Prior to Hubble follow-ups, some skeptics had speculated that the cluster's velocities could have been underestimated or affected by observational noise, leading to an apparent deficit of dark matter. By tracking the clusters with high-resolution imaging and spectroscopy, astronomers confirmed that the velocities are low enough to indicate that the galaxy's gravitational field is dominated solely by its visible stars. In other words, the motion of these clusters is fully consistent with a galaxy that contains almost no dark matter. This confirmation was a pivotal moment. Hubble data provided the independent verification that DF2 is genuinely a galaxy without the invisible mass that shapes nearly every other galaxy we know. Hubble also revealed additional details about DF2's structural characteristics. The galaxy's ultra-diffuse morphology, first observed by Dragonfly, was confirmed with unmatched clarity. Stars are spread across tens of thousands of light-years, and their distribution matches what would be expected for a system with minimal dark matter. Hubble imaging allowed astronomers to calculate the surface brightness profile and confirm that the galaxy is extremely faint, with a central brightness far below that of a typical Milky Way-sized galaxy. This faintness, combined with the distance conformation and the stellar velocities, reinforced the conclusion that DF2 is both large and diffuse, but gravitationally lightweight. Another key contribution of Hubble was the spectroscopic analysis of stellar populations. By examining the light emitted by DF2's stars, astronomers could estimate their ages, metallicities, and distribution within the galaxy. The findings indicated that DF2 contains an ancient population of stars, roughly 9 to 10 billion years old, which aligns with expectations for a galaxy formed in the early universe. The fact that such an ancient system survived for billions of years without a dark matter halo underscored the extraordinary nature of the galaxy and ruled out the idea that it was a temporary or newly formed anomaly. Hubble also played a crucial role in refining the measurements of DF2's globular clusters. These clusters were found to be unusually luminous and massive, consistent with the earlier observations, and their distribution throughout the galaxy was verified to match the predicted dynamics of a system devoid of dark matter. The clusters are orbiting in a gravitational field dominated entirely by the visible stars, confirming that no unseen mass is holding them in place. This precise mapping of the cluster's positions and velocities left little room for doubt. DF2 is both real and extraordinary, a galaxy that exists on the extreme edge of physical possibility. The cumulative effect of Hubble's follow-up was to silence most skeptics. The alternative theories, distance errors, measurement inaccuracies, or projection effects could not account for the full suite of observations. The galaxy's distance, stellar distribution, cluster dynamics, and ancient population all pointed in a consistent direction. DF2 is a Milky Way-sized galaxy, extremely diffuse, hosting massive globular clusters, and critically, almost entirely lacking dark matter. Hubble provided the high-resolution, high-fidelity data necessary to move DF2 from the realm of speculation into the realm of confirmed reality. Beyond confirming the galaxy's existence, Hubble's observations opened new avenues for scientific inquiry. With DF2 verified as real, astronomers began exploring its formation mechanisms, its evolutionary history, and its implications for galaxy formation theories. The galaxy became a laboratory for testing the limits of our understanding of dark matter, a cosmic anomaly that challenges the assumption that all large galaxies require substantial dark matter halos to survive. Every data point gathered by Hubble strengthened the case that DF2 is not an observational fluke, but a genuine, coherent galaxy with properties that defy conventional expectations. Just when astronomers were beginning to grapple with the paradoxical existence of NGC 1052-DF2, another cosmic surprise emerged: the discovery of NGC 1052-DF4, a galaxy that seemed to mirror DF2 in almost every remarkable way. DF4, like its predecessor, is an ultra-diffuse galaxy located in the same galactic neighborhood, roughly 65 million light-years away, in the vicinity of the massive elliptical galaxy NGC 1052. This discovery was significant because it immediately suggested that DF2 was not a one-off anomaly or a statistical outlier. Rather, it hinted at a potentially broader class of galaxies with almost no dark matter. DF4 shares a number of striking characteristics with DF2. It is incredibly faint and diffuse, with its stars so spread out that, much like DF2, background galaxies are visible through it, giving it that ghostly, transparent quality. Its total stellar mass is small relative to its size, yet the galaxy spans tens of thousands of light-years, making it roughly comparable in scale to the Milky Way. Perhaps most astonishingly, follow-up observations revealed that DF4 too has a deficit of dark matter. as inferred from the dynamics of its globular clusters. These clusters orbit the galaxy in a gravitational field that appears to be determined entirely by the visible stars, rather than by an invisible dark matter halo. The globular clusters in DF4 are similarly unusual. They are massive, bright, and disproportionately prominent given the galaxy's low stellar mass. Their presence reinforces the same paradox that DF2 presents. How can such a galaxy form and maintain massive clusters when it lacks the stabilizing influence of dark matter? This twin galaxy provided crucial confirmation that DF2 was not a singular oddity, but part of a pattern that challenges conventional cosmological understanding. The fact that both galaxies exist in the same group suggests that the processes that stripped or prevented the accumulation of dark matter could occur under specific environmental conditions or interactions within a galactic neighborhood. The discovery of DF4 also intensified the debate within the astronomical community. While DF2 initially prompted skepticism and alternative theories, the existence of DF4 made it increasingly clear that galaxies without dark matter are not impossible. They are extremely rare, but real. Having two galaxies with such extraordinary properties located relatively close together implies that the phenomenon might be linked to the local galactic environment, possibly shaped by tidal interactions or stripping processes from nearby massive galaxies like NGC 1052. Such interactions could feasibly remove dark matter from smaller galaxies while leaving their stellar populations largely intact, producing these ultra-diffuse, ghostly systems. Beyond reinforcing the reality of dark matter-deficient galaxies, DF4 also offered a new avenue to test formation and evolutionary hypotheses. Comparisons between DF2 and DF4 allow astronomers to examine whether their properties, stellar mass, cluster populations, velocity dispersion, and overall morphology are the result of a common formation mechanism or coincidental convergence. Observing two such systems provides critical constraints. Any theoretical model must account not only for the existence of a single dark matter-deficient galaxy, but also for multiple examples within the same environment. DF4, therefore, became a natural cosmic laboratory for studying the extremes of galaxy formation and the role of dark matter in shaping stellar systems. The presence of DF4 also underscores the importance of environmental effects in galaxy evolution. Both DF2 and DF4 reside in a relatively dense region of space, near a massive elliptical galaxy, which supports the hypothesis that interactions with larger neighbors may play a critical role in stripping away dark matter. Such interactions could involve gravitational tidal forces or violent past mergers, selectively removing dark matter while leaving stars and clusters largely intact. The discovery of a second, similar galaxy bolsters this line of reasoning, suggesting that these unusual galaxies are not random anomalies, but rather products of specific, high-energy interactions within galactic groups. Additionally, the twin nature of DF2 and DF4 raises broader questions about the frequency and distribution of ultra-diffuse, dark matter-deficient galaxies. If these galaxies are found in clusters or groups with massive companions, it might indicate that they are not solitary oddities, but rather part of a wider class of objects that conventional surveys have historically overlooked due to their faintness and diffuse nature. The combined study of DF2 and DF4 allows astronomers to refine observational techniques such as deep imaging and velocity measurements to identify similar systems elsewhere in the universe. This could ultimately reveal whether DF2 and DF4 are exceptional, rare outliers, or the first glimpses of a previously underappreciated population of galaxies. The discovery of DF4 also had a psychological and conceptual impact on the astrophysical community. DF2 had initially been treated as an extraordinary fluke, raising debates about the validity of observations or potential errors in distance and velocity measurements. DF4's existence, however, legitimized the phenomenon, providing independent confirmation that galaxies can indeed survive without the expected dark matter component. It transformed DF2 and DF4 from curiosities into serious subjects for theoretical modeling, forcing cosmologists to rethink assumptions about dark matter's ubiquity and its necessity for galaxy formation. The discovery of NGC 1052-DF2 and its twin, NGC 1052-DF4, has had profound implications for cosmology, particularly because they challenge one of the foundational assumptions of modern astrophysics, the universality of dark matter in galaxy formation. For decades, the lambda cold dark matter model has been the prevailing framework for understanding the universe. According to this model, dark matter forms the gravitational scaffolding around which galaxies coalesce. Without it, stars and gas would struggle to clump together, and galaxies as we know them would likely fail to form or rapidly disperse. DF2 and DF4, however, demonstrate that large, Milky Way-sized galaxies can exist with virtually no dark matter, a reality that pressures the standard model and forces theorists to reconsider its limitations. In standard cosmology, dark matter halos are essential for stabilizing galaxies and regulating their internal dynamics. They dominate the gravitational potential, holding stars in orbit and preventing them from dispersing into intergalactic space. In DF2 and DF4, the total gravitational mass is almost entirely accounted for by visible stars, which is extremely unusual. This means that, contrary to conventional theory, the galaxy's stars have somehow remained bound for billions of years without the expected dark matter to maintain cohesion. The very existence of these galaxies suggests that either the processes governing galaxy formation are more varied than previously thought, or that there are mechanisms that allow stellar systems to survive under conditions that standard cosmology would deem impossible. The presence of these galaxies also raises questions about the relationship between dark matter and stellar mass. In most observed galaxies, there is a tight correlation between the two. Larger galaxies generally contain more dark matter, and ultra-diffuse galaxies are usually embedded in massive halos that compensate for their low stellar mass. DF2 and DF4 break this pattern entirely, showing a large spatial extent but extremely low total mass, with a dark matter component that is either negligible or missing entirely. This challenges the notion of universality in galaxy formation and suggests that stellar populations might sometimes exist independently of their expected dark matter scaffolding. If such systems are more common than previously thought, it could indicate a fundamental gap in our understanding of how galaxies assemble and evolve. Another consequence is that DF2 and DF4 prompt reconsideration of the role of dark matter in globular cluster formation. Both galaxies host unusually massive globular clusters, which are typically thought to require the deep gravitational potential provided by dark matter to form and survive. The survival of these clusters in a dark matter deficient environment suggests that cluster formation mechanisms may be more robust and less dependent on dark matter than assumed, or that there are unknown processes capable of producing such systems under extreme conditions. This discovery therefore puts pressure not only on galaxy formation models, but also on theories of star cluster dynamics and evolution. DF2 and DF4 also force a re-evaluation of the limits of the lambda cold dark matter model at smaller scales. While the model has been remarkably successful at explaining large-scale cosmic structures, such as galaxy clusters and the cosmic microwave background, discrepancies at the scale of individual galaxies, sometimes referred to as the small-scale crisis, have already been noted. These galaxies exacerbate that crisis by providing concrete examples of stellar systems that appear to operate outside the predicted behavior of lambda cold dark matter model. They suggest that while dark matter dominates the universe at large scales, its influence on galaxy formation might be more nuanced, variable, or context-dependent than previously appreciated. The anomalies presented by DF2 and DF4 also open the door to testing alternative theories of gravity. If galaxies can form and persist without dark matter, it raises the possibility that our understanding of gravitational dynamics at galactic scales may need revision. Models like modified Newtonian dynamics, MOND, which attempt to explain galactic rotation curves without invoking dark matter, gain relevance in this context. These galaxies become a proving ground for evaluating whether deviations from Newtonian and Einsteinian gravity could account for their stability, offering an opportunity to explore the boundaries between dark matter and modified gravity explanations. Importantly, these galaxies highlight the complex interplay between theory and observation in cosmology. The lambda cold dark matter model predicts that galaxies without dark matter should be extraordinarily rare or even impossible. The fact that two such galaxies have been observed in the same local group challenges theorists to account for not just one, but multiple counterexamples. It forces the community to explore rare formation pathways, such as tidal stripping or mergers, that could remove dark matter while leaving stars intact, and to assess whether these pathways are consistent with the overall statistical distribution of galaxies in the universe. The existence of DF2 and DF4 also has implications for our understanding of cosmic structure evolution. If these galaxies can survive without dark matter, it raises questions about the survival timescales of low-mass, ultra-diffuse galaxies in different environments. Could there be other dark matter-deficient galaxies hidden in the universe, waiting to be discovered? If so, they might represent a new class of galactic systems, one that requires revisions to galaxy formation models, cosmological simulations, and our broader understanding of how mass and gravity interact on small scales. One of the most intriguing ways astronomers have attempted to reconcile the existence of NGC 1052-DF2 and DF4 with our understanding of the cosmos is through the modified Newtonian dynamics, MOND, hypothesis, a theory that challenges the conventional role of dark matter. MOND, first proposed in the early 1980s by physicist Mordechai Milgram, suggests that the laws of gravity may behave differently at extremely low accelerations, precisely the regime in which galaxies like DF2 operate. Instead of requiring an invisible dark matter halo to explain galactic rotation curves, MOND modifies Newton's law of gravity, positing that at very small accelerations, gravitational attraction weakens more slowly than classical physics predicts. In the context of ultra-diffuse, low-mass galaxies, this theory offers an alternative explanation for why their stars and globular clusters remain bound, despite the apparent lack of dark matter. Under MOND, the apparent discrepancy between the visible mass of a galaxy and the gravitational forces inferred from the motion of its stars is not caused by missing dark matter, but by a fundamental change in how gravity operates at low accelerations. For galaxies like DF2, where the acceleration of stars is extraordinarily weak due to the galaxy's diffuse nature, MOND predicts that the gravitational pull from the visible stellar mass alone could be sufficient to maintain structural stability. In other words, MOND offers a mechanism by which a galaxy could survive without a dark matter halo, effectively reproducing the observed dynamics of DF2 and DF4 without invoking an invisible mass component. This is a radical shift from the conventional paradigm, suggesting that what we interpret as a missing mass problem may instead be a limitation in our understanding of gravity itself. The application of MOND to DF2 and DF4 is particularly compelling because these galaxies represent extreme test cases. Most galaxies studied under MOND still contain significant amounts of visible and inferred dark matter, making it difficult to distinguish between standard gravity with dark matter and modified gravity scenarios. DF2, with its near-total absence of dark matter, provides a clean laboratory. Its dynamics are dominated almost entirely by the observed stellar mass, placing it directly in the low acceleration regime where MOND predictions diverge most strongly from Newtonian expectations. By applying MOND equations to the motions of the globular clusters in DF2, researchers can test whether modified gravity alone is sufficient to account for the galaxy's stability. One challenge with MOND, however, is that while it can explain the dynamics of individual galaxies like DF2, it struggles to reconcile with the larger scale structure of the universe. The lambda-cold dark matter model, which incorporates dark matter, successfully explains phenomena such as the cosmic microwave background, large-scale galaxy clustering, and gravitational lensing at scales far beyond individual galaxies. MOND, by contrast, is primarily designed to address galaxy-scale discrepancies, and its ability to account for these cosmological phenomena is limited without additional modifications or assumptions. Nonetheless, the peculiar properties of DF2 and DF4 have reinvigorated interest in MOND as a potential complement to standard models, at least in certain contexts. Another aspect of MOND's relevance is its ability to predict the relationship between stellar mass and velocity dispersion in galaxies. In conventional Newtonian gravity with dark matter, the velocity of stars or globular clusters depends on both visible and dark matter. In MOND, the observed velocities are determined solely by the stellar mass, modified by the acceleration-dependent gravitational law. Remarkably, preliminary studies suggest that the velocity dispersions measured in DF2 and DF4 could be consistent with MOND predictions, hinting that these galaxies may indeed be operating in a regime where modified gravity dominates. This provides a tantalizing, though not definitive, alternative to the standard dark matter explanation. Critics of MOND point out that while it may explain DF2 and DF4, it does not solve the full spectrum of dark matter puzzles, and it may require additional assumptions to remain consistent with other observations. For example, MOND alone cannot easily account for the dynamics of galaxy clusters or the lensing effect seen on large scales, where dark matter appears to play a dominant role. Some proponents suggest hybrid models, in which MOND operates at galactic scales, while dark matter exists at larger cosmic scales, allowing both frameworks to coexist. DF2 and DF4 thus serve as critical testing grounds for these theories, offering a rare opportunity to observe systems that are dominated by extreme conditions where the limits of both Newtonian gravity and dark matter assumptions are stretched to the maximum. The existence of DF2 and DF4 has not definitively proven MOND correct, nor has it disproven dark matter. What it has done is provide a unique observational challenge, forcing scientists to consider whether the laws of gravity are truly universal, or whether they might exhibit unexpected behaviors under specific conditions. If MOND can successfully account for the stability and dynamics of these galaxies, it would represent a major paradigm shift, suggesting that our understanding of fundamental physics may be incomplete. Conversely, if future observations reveal inconsistencies with MOND predictions, it strengthens the case for dark matter and highlights the extraordinary processes that must have led to these galaxies' formation. In essence, the modified Newtonian dynamics hypothesis offers a provocative and elegant alternative explanation for the mysteries posed by DF2 and DF4. It provides a mechanism for galaxies to remain coherent without dark matter, directly addressing one of the central paradoxes of these systems. At the same time, it challenges astronomers to reconcile galaxy-scale anomalies with cosmological observations, sparking renewed debate over the nature of gravity, the role of dark matter, and the fundamental laws that govern the universe. Whether or not MOND ultimately proves correct, its application to DF2 underscores the creative and flexible thinking required to understand a universe that continues to surprise us at every turn. One of the leading theories proposed to explain the enigmatic properties of NGC 1052-DF2 and its twin DF4 is that these galaxies may have lost their dark matter through a process known as tidal stripping. In this scenario, DF2 was not born completely devoid of dark matter. Rather, it initially formed within a conventional dark matter halo like most galaxies. Over billions of years, gravitational interactions with nearby massive galaxies, most notably the elliptical giant NGC 1052, could have pulled away the galaxy's dark matter, leaving behind only its visible stellar population and a few massive globular clusters. This hypothesis offers a plausible mechanism for producing a galaxy that is both ultra-diffuse and almost entirely lacking dark matter, while remaining consistent with conventional cosmological principles. Tidal stripping occurs when a smaller galaxy passes near a much larger one, and the gravitational forces exerted by the massive neighbor overwhelm the smaller galaxy's gravitational binding energy. Dark matter, being less centrally concentrated than the stars, is particularly vulnerable to this process. In DF2's case, simulations suggest that a sufficiently close encounter with NGC 1052 or another nearby massive galaxy could have stripped away most or all of its dark matter halo. The stars, being more centrally concentrated and tightly bound, would survive the encounter, remaining in a diffuse, ghostly configuration that matches the observed structure of DF2. Globular clusters, which orbit relatively close to the galaxy's center, could also remain intact, explaining why DF2 hosts these unusually massive clusters despite the apparent absence of dark matter. This stripped galaxy hypothesis aligns with environmental evidence. Both DF2 and DF4 are located within the same group of galaxies, near massive companions. Such environments are known to facilitate tidal interactions and mergers, which can profoundly reshape smaller galaxies. Observations of galaxy clusters frequently reveal ultra-diffuse galaxies with unusually low dark matter content, supporting the idea that close encounters can effectively remove dark matter while leaving stars relatively undisturbed. In this context, DF2 and DF4 may represent extreme cases of an already observed phenomenon, where tidal forces have selectively stripped away dark matter to an extraordinary degree. Computer simulations have been instrumental in testing this theory. Researchers have modeled interactions between ultra-diffuse galaxies and massive neighbors, finding that dark matter can be preferentially stripped from a galaxy while leaving its stellar component largely intact, particularly if the encounter is close and repeated over time. These simulations produce galaxies with properties strikingly similar to DF2: low total mass, high ratios of visible stars to dark matter, and large, diffuse spatial distributions. The simulations also suggest that surviving globular clusters could maintain relatively stable orbits even after the halo is removed, offering a natural explanation for DF2's massive clusters that shouldn't exist in a conventional dark matter deficient scenario. However, While tidal stripping is a compelling explanation, it is not without challenges. One issue is timing. The stripping must occur early enough in the galaxy's history to allow it to stabilize in its current configuration, but not so violently as to disrupt the stellar population. Additionally, the stripping must be extreme enough to remove nearly all dark matter, which is unusual even in dense environments. This has led some astronomers to suggest that DF2 may have undergone multiple close encounters or a particularly catastrophic interaction, a scenario that is rare but not impossible. The fact that DF4 exhibits similar properties further supports the idea that a specific environmental mechanism, such as repeated tidal stripping in a dense group, may be responsible for producing these exceptional galaxies. Observational evidence also provides subtle hints supporting the stripped galaxy hypothesis. DF2's elongated, diffuse morphology could be a remnant of gravitational stretching during close interactions, and the alignment of its globular clusters might reflect the orbital dynamics imposed by tidal forces. Some studies have even suggested that trails of stripped material or faint stellar streams could exist in the surrounding space, remnants of the galaxy's lost dark matter halo or loosely bound stars that escaped during the stripping process. Future observations, particularly deep imaging and precise stellar motion measurements, may help identify these features and confirm whether DF2 is indeed a stripped remnant. This theory also has the advantage of remaining largely compatible with the lambda cold dark matter model of cosmology. Unlike MOND, which requires modifications to fundamental gravitational laws, tidal stripping operates entirely within the standard framework. It does not require a galaxy to form without dark matter, nor does it challenge the universality of dark matter on cosmic scales. Instead, it highlights the complexity and diversity of galactic evolution, showing that even within the conventional paradigm, extreme interactions can produce galaxies that appear to defy the rules while still obeying the underlying physics. Yet, despite its appeal, the stripped galaxy hypothesis does not fully solve all of DF2's mysteries. Questions remain about the origin of its massive globular clusters, the precise mechanism that removed so much dark matter without dispersing stars, and the rarity of such galaxies. Why don't we observe more DF2-like systems if tidal stripping is possible? These unanswered questions make DF2 and DF4 not just anomalies to explain, but active laboratories for testing galaxy formation theories, environmental effects, and the limits of gravitational interactions. NGC 1052-DF2 has rapidly evolved from a cosmic curiosity into a powerful natural laboratory, offering astronomers an unparalleled opportunity to study galaxy formation, evolution, and the mysterious nature of dark matter under extreme conditions. Most galaxies observed in the universe contain dark matter halos that dominate their gravitational potential, meaning that the behavior of stars and star clusters is largely governed by this invisible mass. DF2, however, breaks this rule, presenting a galaxy in which the visible stellar component alone accounts for nearly all of the gravitational forces at work. This unique configuration allows scientists to isolate the effects of ordinary matter, stars, gas, and star clusters, without the confounding influence of dark matter, something that is virtually impossible in most other galaxies. One of the key areas where DF2 functions as a cosmic laboratory is in testing theories of dark matter distribution and necessity. Because the galaxy appears to lack dark matter, it provides a counterexample to the long-standing assumption that dark matter is essential for galaxy stability. By carefully observing the motions of its stars and massive globular clusters, astronomers can measure the galaxy's total gravitational mass directly, providing an empirical test of the minimal mass needed for galaxy cohesion. Such measurements have implications not only for dark matter deficient galaxies, but also for our understanding of the lower limits of galaxy formation in general. DF2 effectively allows researchers to observe a pure stellar system at a scale normally dominated by invisible matter. DF2 also offers a rare opportunity to study the dynamics and survival of globular clusters in extreme conditions. The galaxy's unusually bright and massive clusters orbit within a shallow gravitational potential, entirely determined by the visible stars. This scenario is nearly impossible to replicate in simulations of standard galaxies, where dark matter provides most of the binding force. By tracking the motions of these clusters, astronomers can test theoretical models of cluster formation, orbital evolution, and long-term stability in a galaxy where gravitational interactions are governed purely by baryonic matter. The insights gained from DF2 could help refine our understanding of how globular clusters form in both typical and atypical galactic environments. Another aspect of DF2's value as a laboratory lies in its ultra-diffuse morphology. Most Milky Way-sized galaxies are dense and compact, with stellar populations tightly bound within a massive halo. DF2, however, is spread across tens of thousands of light-years, with stars so faint and sparse that background galaxies are visible through it. This extreme structure allows scientists to study how galaxies can maintain structural coherence under minimal gravitational confinement, providing empirical constraints for models of stellar dynamics, tidal interactions, and internal stability in low-density systems. By examining DF2's shape, stellar density profile, and distribution of mass, researchers can test the limits of what constitutes a stable galaxy, exploring a regime rarely observed elsewhere in the universe. DF2 also serves as a test case for alternative gravity models like modified Newtonian dynamics, MOND. Since the galaxy's gravitational field is dominated almost entirely by visible stars, its dynamics occur in the low acceleration regime where MOND diverges most from Newtonian predictions. By comparing the measured velocities of stars and clusters with the predictions of MOND and conventional dark matter-based models, astronomers can evaluate the applicability of alternative gravity theories in a real, observable system. DF2 thus provides a rare empirical benchmark for distinguishing between competing theories of galactic dynamics, an opportunity that is otherwise difficult to obtain because most galaxies are deeply embedded in dark matter halos. Beyond testing gravitational physics, DF2 offers insights into galaxy formation and environmental effects. Its location near massive galaxies like NGC 1052 suggests that tidal interactions may have played a role in shaping its unusual properties. By studying DF2, astronomers can examine the processes by which galaxies are stripped of their dark matter and potentially altered in size, shape, and stellar distribution. Observing DF2's globular clusters, stellar populations, and morphology allows scientists to reconstruct the galaxy's evolutionary history, offering a window into how galaxies interact with their environment and how extreme conditions can produce configurations that defy standard expectations. DF2 also has implications for understanding the diversity of the galactic population in the universe. While most galaxies adhere to predictable correlations between size, mass, and dark matter content, DF2 occupies an extreme outlier position, challenging these scaling relations. Studying DF2 helps astronomers determine the limits of these relationships and identify the factors that can produce deviations. This in turn informs surveys of faint, diffuse galaxies, helping researchers develop more accurate models of the full spectrum of galactic structures in the cosmos. In addition, DF2's ancient stellar population, estimated to be roughly 9 to 10 billion years old, provides a laboratory for stellar evolution in low-gravity environments. Without a dominant dark matter halo, the stars in DF2 evolve under weaker overall gravitational forces, potentially affecting the dynamics of stellar interactions, cluster formation, and even the retention of gas and dust over cosmic time. Studying these effects could yield new insights into how galaxies evolve under extreme conditions and how stellar populations adapt to low-density environments. Ultimately, DF2 exemplifies how a single, unusual galaxy can provide multiple avenues of scientific investigation, from testing dark matter theories and modified gravity to examining galactic evolution and environmental effects. Its unique combination of properties, ultra-diffuse size, low stellar mass, massive globular clusters, and near-total absence of dark matter, makes it a cosmic laboratory unlike any other, offering an extraordinary opportunity to challenge, refine, and expand our understanding of the universe. Each observation of DF2 pushes the boundaries of astrophysics, providing real-world data to confront theoretical models and inspiring new questions about the formation, survival, and diversity of galaxies in the cosmos. The existence of NGC 1052-DF2 and its twin DF4 has profound broader implications for the dark matter debate, forcing astronomers and cosmologists to reconsider long-held assumptions about the necessity of dark matter for galaxy formation and stability. Traditionally, dark matter has been considered the invisible scaffolding of the universe, the gravitational glue that allows galaxies to coalesce, maintain their shape, and survive for billions of years. Without it, conventional theory predicts that stars in a galaxy would drift apart, unable to remain gravitationally bound. Yet, DF2 and DF4 challenge this notion. These galaxies exist, are coherent, and appear dynamically stable, despite having little to no dark matter. Their very existence raises the question: could some galaxies survive entirely without dark matter? If DF2 and DF4 are representative of a broader, albeit rare, class of galaxies, it suggests that the universe may permit alternative pathways for galaxy formation, ones that do not require dark matter as an essential component. In these systems, the visible stellar mass alone, sometimes supplemented by tightly bound globular clusters, provides enough gravitational cohesion to maintain structure. This realization expands the possible diversity of galaxies, implying that while dark matter is overwhelmingly dominant in most systems, it may not be universally necessary for the survival of every galaxy. These galaxies thus act as natural experiments, showing that the cosmic rules governing galaxy formation may be more flexible than previously assumed. The broader implications extend beyond the mere survival of galaxies. DF2 and DF4 provoke re-evaluation of scaling relations long thought to be universal in astronomy. Relationships like the Tully-Fisher relation, which links a galaxy's rotation velocity to its luminosity, or the mass-to-light ratios commonly observed in galaxies, are typically understood within the framework of dark matter. Ultra-diffuse galaxies, with little to no dark matter, defy these relations, demonstrating that such correlations are not absolute laws, but rather tendencies that may fail under extreme conditions. By challenging these empirical laws, DF2 and DF4 highlight the need to refine our theoretical models to accommodate the full diversity of galactic systems. Another significant implication concerns the formation and evolution of galaxies in dense environments. Both DF2 and DF4 exist in proximity to a massive galaxy, NGC 1052, and their properties suggest that environmental effects, such as tidal interactions, stripping, or mergers, may play a critical role in producing galaxies deficient in dark matter. If these mechanisms are common in certain environments, it implies that the dark matter content of galaxies may not be solely determined at birth, but can be dramatically altered over cosmic time by gravitational interactions. This shifts some focus away from intrinsic galaxy formation models toward environment-driven evolution, highlighting the dynamic and complex nature of galaxy development. DF2 and DF4 also have profound consequences for the interpretation of dark matter observations on cosmological scales. While the lambda cold dark matter model successfully explains large-scale structures and the cosmic web, the discovery of dark matter deficient galaxies suggests that local deviations from the expected dark matter distribution can occur, potentially complicating attempts to map dark matter solely based on galactic mass or rotation curves. These anomalies provide both caution and opportunity. They remind cosmologists that dark matter may not manifest uniformly, and that outliers must be accounted for in simulations and theoretical predictions. Understanding these exceptions could refine models of dark matter behavior and improve our understanding of the underlying physics governing cosmic structure. Furthermore, DF2 and DF4 challenge assumptions about the role of dark matter in star cluster survival and formation. Both galaxies host unusually massive globular clusters, which, in conventional theory, are thought to require the gravitational stability provided by a dark matter halo. Their presence in galaxies with negligible dark matter implies that cluster formation and longevity can occur under much less stabilizing influence than previously thought. This forces a re-evaluation of the interplay between baryonic matter and dark matter in shaping both galaxy and cluster dynamics, suggesting that stars and clusters may be more resilient to low-gravity environments than once believed. The broader implications also extend to alternative theories of gravity. While dark matter remains the dominant explanation for cosmic mass discrepancies, systems like DF2 and DF4 lend credence to the idea that modifications to Newtonian dynamics or general relativity could account for some of the anomalies observed at galactic scales. If such galaxies are stable without dark matter, it raises the question of whether our understanding of gravity might be incomplete, at least in certain low acceleration regimes. Consequently, DF2 and DF4 serve as critical empirical benchmarks for testing both conventional and alternative models, highlighting regions where theory and observation intersect in surprising ways. Even with a variety of proposed explanations, from tidal stripping to modified gravity theories, NGC 1052-DF2 continues to confound astronomers, embodying a mystery that refuses to fit neatly into established models of galaxy formation and evolution. Despite years of observations and detailed analysis, the galaxy's combination of ultra-diffuse structure, minimal dark matter, massive globular clusters, and coherent stellar dynamics remains an extraordinary enigma. It challenges the conventional wisdom that dark matter is the essential framework for galaxy cohesion, and forces scientists to confront the possibility that our understanding of what constitutes a normal galaxy is incomplete. One aspect that continues to puzzle researchers is the apparent stability of DF2 without dark matter. Standard cosmological models predict that a galaxy of its size and mass should disperse over time if not held together by an invisible halo of dark matter. Yet DF2 has persisted for billions of years, maintaining its structure and hosting massive star clusters without disintegrating. This presents a paradox. How can a galaxy maintain gravitational coherence under such conditions? The survival of DF2 suggests that either there is an unknown stabilizing mechanism at work, or that the range of possible galactic configurations allowed by physics is broader than previously thought. The galaxy's ultra-diffuse morphology adds another layer of intrigue. Its stars are spread so thinly that background galaxies can be seen through it, creating the appearance of a nearly transparent stellar system. Such extreme diffusion is uncommon for galaxies of DF2's size, and it raises questions about the processes that can generate and maintain such structures. How did the stars manage to spread so widely without causing the galaxy to fall apart? Are interactions with nearby galaxies solely responsible, or did DF2's initial formation conditions play a critical role? These questions remain unresolved, highlighting the limits of our observational and theoretical frameworks. Adding to the mystery are DF2's massive globular clusters, which seem anomalously bright and dense compared to what is expected for a galaxy with so little dark matter. In most galaxies, the survival and stability of globular clusters are closely tied to the gravitational influence of dark matter. In DF2, however, these clusters have endured in a shallow gravitational potential, defying expectations. Their existence raises important questions about star cluster formation and evolution in extreme environments, suggesting that our models for these processes may need revision to account for such exceptional cases. Even environmental explanations, like tidal stripping by NGC 1052, while compelling, do not fully resolve the mystery. Stripping could explain the removal of dark matter, but it would require finely tuned conditions to preserve the stellar component and massive clusters without disruption. Furthermore, DF4, a galaxy with very similar properties, exists in the same group, implying that such conditions may not be as singular as once thought. This repetition raises new questions. How common are such galaxies? Are they rare anomalies, or is there an unrecognized mechanism producing them in specific cosmic environments? The modified gravity hypothesis also offers potential answers, particularly in explaining DF2's dynamics without dark matter, but it too leaves unanswered questions. MOND and similar theories can reproduce some aspects of the galaxy's behavior, yet they do not fully reconcile DF2 with other observational constraints, especially on larger cosmic scales. The galaxy, therefore, stands at the intersection of competing theories, serving as a test case that strains both conventional dark matter models and alternative gravity frameworks. Another compelling dimension of the mystery is the implication for galaxy formation history. DF2 forces astronomers to consider that galaxies may evolve along unexpected pathways, including the possibility of forming in environments or through processes previously thought implausible. Whether through interactions, mergers, or internal dynamics, DF2 demonstrates that the universe can produce systems that seem to break the rules derived from studying more typical galaxies. This challenges scientists to expand their models and embrace the diversity and complexity of galactic evolution in ways that account for extreme outliers. Ultimately, the enduring mystery of DF2 underscores a larger lesson about the universe. Even phenomena that appear to violate the laws of physics often illuminate gaps in human understanding rather than actual contradictions in nature. DF2 is not just an anomaly to be catalogued, it is a window into the unexpected, a natural laboratory for testing fundamental principles, and a reminder that the cosmos is far more diverse and surprising than our models might suggest. Each observation, measurement, and theory surrounding DF2 pushes the boundaries of astrophysics, compelling scientists to refine existing paradigms, explore new mechanisms, and accept that some aspects of the universe remain tantalizingly mysterious. In this sense, DF2 is emblematic of the scientific process itself. It challenges assumptions, sparks debate, and drives inquiry forward. It shows that even in a universe seemingly governed by well-understood laws, there are still regions of extreme oddity where the ordinary rules do not seem to apply, and where the boundaries between the known and the unknown are sharply drawn. DF2 continues to stand as one of the most compelling reminders that the universe is not only stranger than we imagine, it is stranger than we can imagine, defying our expectations and inspiring continued exploration. As we draw our exploration of NGC 1052-DF2 to a close, it becomes clear that this galaxy is far more than a collection of stars. It is a cosmic enigma, a silent testament to the universe's boundless capacity for surprise. Galaxies like DF2 challenge our most fundamental assumptions about the nature of matter, gravity, and the processes that govern galaxy formation. They force us to confront the uncomfortable truth that even the frameworks that have guided decades of astronomical research are not immune to exceptions, and that the cosmos has a way of producing structures that defy the neat categories we try to impose. In the case of DF2, we see a system that refuses to conform to the gravitational paradigms we take for granted. A galaxy that exists with almost no dark matter, yet remains coherent, with massive globular clusters orbiting serenely in its shallow gravitational field. This extraordinary galaxy reminds us that the universe does not always play by our rules. Our models of cosmology and galaxy formation, while remarkably successful in explaining most observations, are based on the patterns we have observed in the majority of cases. DF2 and galaxies like it exist on the fringes of these patterns, occupying a realm where the unexpected becomes reality. Their existence serves as both a humbling challenge and an exhilarating opportunity. A challenge because it exposes the limitations of our current understanding, and an opportunity because it provides a natural laboratory in which to test theories, refine models, and push the boundaries of astrophysics. Beyond its scientific significance, DF2 evokes a profound sense of cosmic wonder. It stretches the imagination to consider how such a delicate, ghostly structure can persist across billions of years without the unseen scaffolding that we have long believed is essential. Its ethereal transparency, the survival of its massive star clusters, and its defiance of the laws as we understand them all, contribute to a picture of the cosmos that is more dynamic, diverse, and mysterious than we might have anticipated. In witnessing DF2, we are reminded that the universe is not a static machine governed by unyielding rules. It is a living, evolving tapestry, full of surprises, anomalies, and phenomena that can stretch human comprehension. Galaxies like DF2 also inspire a sense of scientific humility and curiosity. They teach us that for every principle we think we understand, nature may hold exceptions that compel us to look closer, measure more precisely, and question assumptions that once seemed inviolable. They encourage astronomers to remain vigilant, creative, and open-minded, embracing the anomalies as opportunities rather than obstacles. Each observation of DF2, DF4, and similar galaxies opens new avenues of inquiry, reminding us that the process of discovery is never truly complete, and that the universe will always have hidden corners that elude our expectations. Finally, DF2 serves as a poetic emblem of the cosmos itself, strange, delicate, resilient, and inexplicably beautiful. It challenges our preconceptions, delights our curiosity, and inspires awe at the vastness and complexity of the universe. It is a reminder that the universe is not only a domain of measurable quantities and predictable laws, but also a realm where anomalies persist and where phenomena can occur that make us pause, marvel, and reconsider our place in the cosmic order. NGC 1052-DF2 stands as a testament to the limitless possibilities of nature, a ghostly apparition that exists against the odds, quietly asserting that the cosmos is far stranger richer, and more mysterious than we could ever imagine. In the end, galaxies like DF2 are more than objects of scientific study. They are beacons of wonder, symbols of the unexpected complexity of the universe, and invitations to explore, question, and marvel. They remind us that while we may understand the broad strokes of cosmic structure, there will always be corners of the universe where the rules bend, exceptions arise, and the strange becomes real. As we peer into the depths of space, DF2 whispers a timeless truth. The universe will never cease to surprise, challenge, and inspire. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.